April 1973, Mississippi Delta. A caterpillar D6 crawls toward a levee sand boil on ground that looks dry enough to hold it. Then the surface opens under the tracks. By the time crews understand what the landward side is doing, more dozers are already committed to the same line. To understand why 9 Caterpillar D6E disappeared into a Mississippi levee without ever touching open water, go back to the spring of 1973. The Mississippi River Basin was already under pressure long before the machines arrived. Heavy winter snow across the upper watershed, repeated spring rains, and a river system carrying runoff from thousands of miles upstream had pushed the lower valley into one of the most dangerous flood fights of the era. By April, the problem was no longer simply high water. The problem was time, saturated ground, and a levee system being loaded from one side for days without relief. Along long reaches of the Mississippi, the levee was not a concrete wall. It was an earth structure, built in lifts, widened over time, repaired after earlier floods, and dependent on the strength of the material beneath it as much as the material visible above it. From the riverside, the pressure looked obvious. Brown water rose against the slope and stayed there. But the more dangerous process was often happening under the levee, beyond sight, on the protected land side where crews believed they still had working ground. That hidden process was piping. The reason matters. When a river stands high against a levee for long enough, water does not need to overtop the structure to threaten it. It can move through permeable layers beneath the embankment, following seams of sand and silt under pressure. If that seepage finds an exit on the dry side, it can erupt upward through the ground as a sand boil. To a distant observer, a sand boil can look almost harmless at first. A low dome of muddy water, sometimes only a few feet across, bubbling through a field. But mechanically, it is evidence that the levee is already fighting a pressure path beneath itself. The crews on the Mississippi in 1973 understood sand boils well enough to fear them. They ringed them with sandbags, built containment rings around the boils, and tried to hold back the escaping water by adding weight and back pressure on the landward side. That was standard flood fight practice, but standard practice depends on one condition above all others. The ground around the boil must still be capable of carrying men, trucks, and equipment without collapsing into the very voids the water is creating below. That was where the Caterpillar D6 entered the story. The D6 was not an oversized machine by Mississippi flood standards, but that was exactly why it was used. It was compact enough to work on narrow levee crowns and soft approaches, powerful enough to push fill and shape emergency berms, and common enough in contractor and district fleets to be mobilized quickly. Depending on the exact series in service, a 1970s D6 class tractor typically weighed in the range of roughly 30,000 to 35,000 pounds before the ground carried any additional dynamic load from blade work, turning, or track slip. On paper, that made it a practical levee machine. On the ground, conditions changed everything. The flood fight demanded constant movement. Borrow pits had to be opened, clay had to be hauled, sandbags had to be placed, relief berms had to be shaped fast, often at night, often under orders that changed by the hour as new seepage appeared down the line. The machines were not operating in a clean construction zone. They were working on a structure already under hydraulic attack. Every pass of a dozer added vibration, concentrated load, and delay-sensitive decision-making to ground that might still look intact on the surface, while losing support below. By the time the first D6 were sent toward active boils, the levee was already in a different kind of crisis. The visible emergency was not overtopping water. It was the appearance of boils on the protected side, some small, some aggressive, some carrying enough sand to show that material was being moved from beneath the levee foundation itself. That distinction is critical. Clear seepage can be dangerous. Sandy seepage is worse. Once the escaping water begins transporting foundation material, the question is no longer whether pressure exists. The question is how much of the ground under the levee is being rearranged in real time. Operators approaching those sites were being asked to do something that felt reasonable in the moment. Push more material, build up the ring, raise the berm, get weight where the water is coming through. In many flood fights that works. But a machine arriving at a sand boil is not arriving on ordinary wet earth. It is arriving on ground that may have been undermined from below, with upward water pressure, reducing effective soil strength before the track ever touches it. Mechanically, the problem was this. A crawler tractor spreads its weight better than a truck, but it still depends on sheer strength in the soil beneath both tracks. If the subsurface sand layer has been loosened by upward seepage, and if fine material has already been carried away, the top crust can become a bridge over a voided or semi-fluid zone. It looks like ground, it behaves like a trap. The first machine may crack that crust, the second may break through it. A dozer under blade load is even more vulnerable, because weight shifts forward, ground pressure increases under parts of the track frame, and any attempt to power out can liquefy the support that remains. That is why these machines were defeated by earth instead of water. They were not pushed into the river. They were sent onto a failing pressure system hidden beneath the levee toe. The landward side, the side that should have been safe, had become the weaker side. And once one tractor began to settle, the instinct to save it could place the next one in exactly the same zone of failure. The 9D6 did not vanish in one dramatic instant at one single hole. The losses came as the flood fight escalated, with machines committed to sections where boils multiplied, berm work intensified, and the margin between stable surface and undermined ground kept narrowing. Some settled nose first, some dropped level as the crust gave way under both tracks. Some were still running when the undercarriage disappeared. At that point, the operation changed. The problem was no longer simply holding the levee. It was deciding whether recovery attempts were about to feed the same ground failure that had already taken the first machines. And that is where this story turns from a flood story into a machine story. Because the central question was no longer how high the river stood, it was why experienced crews, using the right class of dozer for levee work, kept losing steel to ground that looked dry enough to work. The answer was buried below the surface, in piping, load, and timing. In the next part, the ground gives way completely. Some crews tried to hold the line anyway. That decision makes sense only if you understand the conditions on site. In a major levee emergency, abandoning a boil field is not a neutral act. If the boil is allowed to run unchecked, the water may continue lifting and carrying foundation sand from beneath the levee. If enough material moves, the embankment above can slump, crack, or fail outright. A dozer sent to the landward toe was not being risked for its own sake. It was being used to buy pressure resistance, one blade load at a time. The first signs of total ground failure were often subtle. A track would settle a few inches deeper than expected. The blade corners would stop riding level. The operator would feel a softness under one side of the seat that did not match ordinary mud. Then the machine would stop responding the way a crawler should. Full throttle would turn into churn without travel. The tracks were no longer climbing against resistance. They were cutting into a surface that had lost its structure underneath. Mechanically, a crawler can sometimes walk out of shallow mud because the track shoes find new material ahead with every rotation. That was not the case here. In a piping zone, the machine was fighting a layer being weakened from below by upward water pressure. The more the operator tried to power out, the more the track action disturbed the crust and broke it apart. What looked like traction loss was really support loss. The machine was not stuck on the ground. It was entering the ground. Then the margin disappeared. Once one D6 had dropped far enough that the belly pan or final drives were near the surface, extraction became a different kind of problem. Pulling a crawler from stable ground is one thing. Pulling 30,000 to 35,000 pounds of steel from liquefied soil beside an active boil is another. Recovery force had to come from another machine, and that meant bringing another machine into the same compromised zone. Every foot closer increased the chance that the rescuer would load the same hidden failure plane. That is how single machine trouble becomes fleet loss. Crews tried the methods available to them. They built up approaches with fill. They attempted pulls from better ground where cable angles allowed. They used additional tractors to gain enough line force to break suction and drag the buried machines back toward firmer material. On paper, the logic was sound. In practice, the site was changing under load. Fresh fill placed over a piping zone does not automatically restore bearing strength. Sometimes it does the opposite, adding weight to a pressure-weakened area and driving the unstable layer wider. A recovery attempt that should have freed a tractor could drive it deeper. A second tractor trying to hold position for the pull could begin settling before the cable even came tight. Operators were no longer reading ordinary mud. They were reading a hydraulic failure under an embankment that still had a river against it on the far side. At that point, the operation changed from machine recovery to levee survival. The priority became keeping enough men and equipment out of the collapse zone to avoid turning a flood emergency into a fatal machinery burial. That decision matters. Bulldozers can be replaced. Operators cannot. In several of the worst levee fights of the 1973 flood, crews reached the same conclusion under slightly different circumstances. If the ground was still boiling, still moving sand, and still unable to support rescue equipment, the trapped machine had to be left where it was. That is how 9 Caterpillar D6s were lost. Not by dramatic river impact, not by a single washout seen from miles away. They were taken by the landward side of the levee, by the side that should have been the safe side, while crews were trying to stop the very process that destroyed the ground beneath them. Some were partially buried and abandoned in place. Some were later stripped or written off because the cost and danger of recovery exceeded the value of the tractor. Some became part of emergency fill zones that had to remain undisturbed while the flood crest passed. The reason this happened is not mysterious. The machines entered the crisis long before the crisis became visible. By the time a sand boil is large enough to demand crawler work at close range, the hydraulic conditions that created it are already established below the levee. Water under pressure had found a path through permeable material. Fine particles had already been mobilized. The crust on the protected side was no longer a trustworthy indicator of bearing capacity. The D6s were fighting physics, not just workload, and yet the crews did prevent wider disaster in many sectors of the 1973 flood. That is the part these machine stories often lose. A lost tractor stands out in photographs and memory because steel is visible. What it was trying to prevent is less visible. Behind every abandoned dozer on a levee line was a calculation about towns, farms, roads, rail lines, and hours of remaining margin before a much larger breach. The machines were committed because the stakes downstream were larger than the machine itself. After the flood receded, the damaged levee sections were studied more carefully. Engineers looked again at foundation conditions, seepage paths, relief berm performance, and the limitations of emergency equipment working on saturated embankment tows. The lesson was not that bulldozers had no place in flood fighting. The lesson was narrower and harsher. Heavy equipment can place emergency material fast, but no amount of horsepower can restore soil strength that upward seepage has already destroyed. Once piping undermines the foundation, the machine is operating on borrowed ground. That understanding shaped later flood practice. Better boil monitoring, more disciplined standoff distances, improved use of ring levees and weighted blankets, and more caution about sending heavy track machines directly into active seepage zones all came from hard experience. Flood control is often described in terms of levee height and river stage, but many failures are decided below grade, in sand seams, pore pressure, and the invisible movement of fines. The 1973 losses made that impossible to ignore. The Caterpillar D6 itself went on working across America for decades after that flood. It remained one of the most useful crawler classes ever built for mixed earthmoving, roadwork, forestry, and embankment operations. That is part of what makes this story worth remembering. The machine was not wrong for the job in general. It was wrong for ground that had already ceased to behave like ground. On paper, the D6 could do exactly what the crews needed. On site, the levee tow had become something else entirely. The machines are gone now. The boil fields were repaired, the slopes rebuilt, the flood marks faded, and most of the public memory of that spring narrowed to river stages and evacuation maps. But the operational lesson remains. A crawler tractor can push against clay, rock, snow, timber, and debris. It cannot negotiate with a foundation being emptied from below. If this kind of machine history matters to you, subscribe. This channel is built for stories exactly like this. One machine, one place, one decision, and the consequences that followed. And this was not the last time unstable ground defeated a bulldozer before water ever reached the blade.